Assalamu alaikum. Welcome to the lecture. Today we'll talk about determinants. Okay. Now, determinants is a very important quantity in linear algebra. In fact, it's a scalar quantity that can be computed from the elements of a square matrix. Okay, and encodes certain properties of the linear transformation described by that square matrix. Okay, generally, if this square matrix is noted by A, the determinant of this square matrix is noted by determinant of A. Okay, now generally, geometrically, we will see at the end of his lecture, it can be viewed as the area scaling and the volume scaling factor of the linear transformation described by this matrix A. And generally, this is also the signed volume of the n-dimensional parallelopiped spanned by the column or the row vectors of this matrix A. Determinant is positive or negative according to whether this linear transformation and mapping preserves or reverses the orientation of the space. Okay. Now, before we talk about the physical significance of determinants, let's discuss how we can find the determinant. Okay, so for a square matrix, let's say, which is n cross n, right? Determinant of this matrix can be defined by, let's say, before that, let's say A is composed of elements, which is Aij. So actually is the sum of n terms. Of the form plus minus A1j, right? Determinant of Aij with plus and minus signs alternating where the entries A11, A12 up to A1n are from the first row of A. So we can expand this in this term like determinant of A, because the sum of n terms is nothing but equals to A11 determinant of A11 minus A12 determinant of A12 plus so on and so forth. It becomes minus 1 plus n A1n determinant of A1n. Okay, now can be written as j is equals to 1 to n minus 1 into 1 plus j A1j determinant of A1j. Okay, now in this one, these small a's are the elements of the matrix A, which is A is equals to A11, A12 to A1n. Okay, this is A21, A22 up to A2n, and AN1 up to ANN. Okay, now similarly, the A11 matrix is that you get by deleting the first row and the first column. Okay, so the remaining terms that you can write here is A22 to up to A2n, and again AN2 to a n n. Okay, similarly if I say if I want to find a12, so you can write a12 as a12 as, so you delete the first row and the second column. Okay, so that becomes a11, a21 up to a, sorry, first row and the second column, that becomes a11, a21, an1, and again you skip that one, it becomes a13, sorry, a21, my bad. Okay, and this becomes a23, a33, and an3 up to a1n, a2n, and a. Okay, let's do an example to illustrate what we have just said. Let's say a is equals to 1, 5, 0, 2, 4, minus 1, 0, minus 2, 0. Okay, now this can be expanded. Determinant of a can be expanded in a form like this, right? So you start with j is equals to 1 to n minus 1 to I 1 plus j a1j and a1j, right? And this is determinant of a1j. Okay, now so if I expand this here, that becomes start with the first one, so j is equals to 1, so you get here minus 1 into 1 plus 1, a11, determinant of a11, right? And then you got here plus sign here, minus 1, you got 1 plus 2, a12, determinant of a12, and then you got here is plus 2 minus 1 plus 3, a13, determinant of a13, right? Now determinant of a now can be written as minus, this comes minus 1 square is 1, so a11 here is 1, determinant of a11 is 4 minus 1 minus 2, 0, right? So normally you can use these kind of symbols to illustrate that you are taking the determinant of that matrix, and again you have got here minus, so minus 1 to the power 3 is minus, so a12 here is 5, and determinant a12 would be this row it becomes 2 minus 1, 0 and 0, and again you got here plus a13 is 1, first row, third column, so you got here is 0 times 2, 4, 0 minus 2. Okay, now this comes out to be, we know the determinant of 2 by 2 matrix, which is nothing but if this is a b c d, right? So that is nothing but equals to a d minus b c. So this is a, this is determinant of a. Okay, so we can do here, so multiply this one, and take the subtraction of that. So we got here is 1 times 0 minus 2 minus 5 times 2, 2 times 0 it's 0, and again minus 0, and here again we have 0 times minus 4, and you have got minus 0, right? So our term in this case, this will be 0, this will be 0. The answer here is nothing but equals to minus 2. Okay. Now, now it is more convenient to say define the determinant in a different form, in a slightly different form, which is if A has elements which is Aij, right? You define the ij cofactor of A as Cij, and then you write here is minus 1 into I plus j times determinant of Aij. Now, based on this, the cofactor expansion of A to determine the determinant A can be written as determinant A is nothing but equals to A11 times C11 plus A12 times C12 plus A1n C1n. So this is actually the cofactor expansion across the first row of A. Okay, so this is the cofactor expansion across the first row of A. Now, generally, the determinant of any n by n matrix A can be computed by cofactor expansion across any row or any column. So the expansion across the ith row using the cofactor we can be written as, so determinant of A can be written as A I1 C I1 plus A12 C I2. Then you got here as plus AIN CIN. Okay, so this is the cofactor expansion across a cofactor expansion across the ith row. Similarly, you can write a cofactor expansion down the jth column, which is determinant of A is equals to A 1j C1j plus A2j C2j, and you got here as A and j and C and j. Okay, so the thing here is that we want to summarize is that the determinant of an n cross n matrix, which is A, can be computed by a cofactor expansion across any row or down any column. So this is the main point of this discussion. Okay, so to repeat that again, so we have got this matrix A, right, which is an n cross n matrix. It means a square matrix, and you can find the determinant of this matrix by in the form which is like this. What does it represent? We'll talk about it later, right? but just look at the formula and the method by which you can find this determinant of A, right? So determinant of A actually can be written as A11, which is the element of this square matrix A, and determinant of A11, which is A11 is now, you delete the first row and the first column of that matrix. Okay, so if you delete the first row and the first column, so delete first row, first column, the remaining is this bit. Okay, so that will be A11, right, written over here. Okay, now similarly A12 is the element of this matrix A, and then you got determinant of A12, and again so on and so forth. Okay, so this is the general formula to determine the determinant of this matrix A is this. Okay, now so if you're given we just did an example to illustrate how we can use that formula to determine the determinant of A. So if it's a 3 by 3 matrix here, A is a 3 by 3 matrix, and you use that formula, right? So for a 3 by 3 matrix, we got here J is equals to, actually you want to say J is equals to N is equals to 3, right? So we got here varying J in this formula, so minus 1, so this is 1 plus 1, J is equals to 1. A11 is the element here of this, in this case is 1. Determinant of A1, which is nothing but delete the first row and the first column, right? 4 minus 1 minus 2, 0. This is written over here. And similarly, when you expand that, you will find out this is A12, and determinant of A12 is reading first row, second column, got 2 minus 1, 0, 0, which is written over here. And again, A13, of course, there is a minus 1 times 1 plus 3. A13 in this case is 0, right? And of course you can see here first row and third column, so you're left with 2, 4, 0 and minus 2, right? So when you evaluate those things here, you'll find out the determinant of this matrix, 3 by 3 matrix, is nothing but equals to minus 2, right? Now what you can do is mathematically it is much more convenient to absorb that this thing here, which is the signs and this determinant, because then you can actually write everything in terms of the coefficient of the matrix, right? So so we define by combining this determinant of A11 into, and this sign here, this minus 1 to the power some value in the cofactor, and define this at cofactor ij, and this is nothing but minus 1 I plus j and determinant of aij, right? So you can write the cofactor for any element of the matrix A. So it says you can actually write the cofactor for any element of the matrix, which is ij, nothing but equals to minus 1 of I plus j, and you remove that row, ith row and jth column, and then you write aij, right? And you take the determinant of that matrix, right? So if I simplify this in the cofactor form, this determinant of A, because I have observed this determinant and this term in cofactor, so I can write this straight away as A11 times C11, A12 times C12, and A1 times C1n, right? So this is the cofactor across cofactor expansion across the first row of A. Okay, first row of A. Now because it has got all the first row components of this matrix. Now, we will not prove it here, but you should remember this, right? The determinant of any n cross n matrix A can be computed by the cofactor expansion across any row or down any column. So if this is a matrix A here, right? So you can expand, right, the expansion across this row, across any row, right, in the matrix, or you can use any column to do the cofactor expansion. I mean, you can do that column, or you can try that column, right? The answer will remain the same. We will not prove it here, but this one you should remember, right? So if you're doing the cofactor expansion across the ith row, this is the formula written over here, and if you're doing the cofactor expansion across the jth column, this is the values that is written over here. Okay, now let's do an example and try to find the determinant using cofactor expansion. Let's say a is equals to and demonstrate what we have just said. So again we have the same matrix 1 5 0, 2 4 minus 1 and 0 minus 2 0, right? Now let's try it. Let's try finding the determinant of this matrix A using cofactor expansion across the third row. Okay, now the third row in this case is actually 0 minus 2 and 0, right? So the formula that you can write here is quite very simple, right? So it is A31 C31, right, plus A32 C32, right, and this is A33 and C33. Remember this, C31 is nothing but equal to 331 minus 1 3 plus 1 determinant of A31, right? So with this, in this case, will become, so third row and the first column, right? So it becomes minus 1 times 3 plus 1 determinant and 5 0 4 minus 1, right? Again, C32 can be written as minus 1 3 plus 2 determinant of A32, and again, right, third row second column, right? So we left with minus 1 3 plus 2 here again, which is 1 0 2 minus, and again you got C33 is equals to minus 1 plus 3 plus 3 determinant of A33 is nothing but equals to minus 1 3 plus 3, and you got here the value as 1524. Now I mean, you can see it here because you can have the cofactor expansion across any row or any column, right? To do determine this determinant of A, you want to use the row or column with maximum number of zeros, right? Because then you have you don't have to calculate a lot of values to calculate this determinant of A, right? So in this case, the third row has the maximum number of zeros, right? So in effect, I actually have to calculate this one, right? Because A31 is 0, so I can write 0 times. Okay, let's complete that thing here. So minus 1 to the power 4 is 1, and you got here minus 5. So the answer is minus 5. This thing here is it becomes minus sign here, so minus 1 and 0 again. This becomes plus 1, and this becomes 1 to the power 6 is positive, so 4 minus 10 is minus 6, right? So here what you have is simply as this thing here. So what you get here is 0 times minus 5 plus, so the second element is minus 2, so you got here plus minus 2 times 1 plus again, and you got here 0 times minus 6. The answer here is nothing but equals to minus 2. The same here, same value again as we have calculated using the normal formula of the determinant. Okay, now going back to the point in which I said that you should actually use the cofactor expansion from the point or from any row or any column which has maximum number of zeros, right? So if I, let's say this is a matrix 3 0 0 0 and 0 and minus 7 2 0 0 and 0 8 minus 5 1 2 0 9 7 5 4 and 2 minus 6 3 0 minus 1 0, right? Now see, this actually column has maximum number of zeros. I mean, if you can see, it's I think it's no, not exactly, but so I can use that, right? So determinant of A, I can actually write that as minus in terms of cofactor, right? So a1, so this is the first using the first column, right? So I just keep it here as a11 c11 plus a21 c21 and up to an1 into cn1, right? So all these are actually 0, right? So I just need to compute this a11 and c11. So a11 here is 3 and c11 here, remember this is nothing but equals to minus 1 into 1 plus 1, and determinant of a11, right? So which in this case will become this, right? So 3 into minus square, so minus 1 to the power 2 becomes 1, and determinant of a11 becomes, so you cut this first row and this thing here, you get out 2 0 0 0 minus 5 1 2 0 7 5 4 and 2 3 0 minus 1 and 0. Again you have to find the determinant here, right? Make this one as the point of expansion for to determine this determinant, so that becomes 3 into, again, so this becomes a 2 times, so this is actually you can find the determinant here by eliminating the first row and the first column, in the first column and the first row. So 2 times you got here as 1 5 0 2 4 minus 1 0 2 0, and of course you have to write its place value in terms of minus 1, which is minus 1 times 1 plus 1, right? And again now if I expand this cofactor expansion from this side, right, so it means I only have to calculate this thing here, so that closes out here. Okay, now again 3 into 2 times, and now again here, so you can see here it is best to calculate this this from the third row, right, to have the cofactor expansion from the third row, and we have just calculated it over here in our last slide. So you get it is exactly the same matrix 1 5 0 2 4 minus 1 0 minus 2 0, and for which the determinant is minus 2. So I'm just going to use that, and it becomes 2 into minus 2, and that becomes minus 1 square, so it comes out to be 2 into 2 minus 4, minus 4 into 3 is actually minus 12. The determinant of A is minus 12. Now suppose if you wanted to try to find a determinant using the cofactor expansion across the first row, right? So it means you have to calculate the cofactors for this place value, this place value, this place value, this place value, and this place value, right? And further, because then eventually each cofactor becomes a 4 by 4 cross matrix. So in this case, so 5 terms here, so you got you have to calculate 5 4 by 4 cross matrix determinants, and similarly again each element will further produce a 3 by 3 matrix, so you have to calculate that, and each element then produce a 2 by 2, so it becomes a long chain that you need to calculate before you determine determinant of A. So the best way is actually to use cofactor expansion across that row or column which has zeros in it, or which has most zeros in it. Okay, so let's do another example to illustrate this we have just said. Again here we have been given a problem 5 minus 7 2 and 2 0 3 0 and minus 4, and this is minus 5 minus 8 0 and minus 3, and 0 5 0 minus 6, right? Now again it's we know it's a 4 by 4 cross matrix, and it's a quite a bit big matrix, right? So what you can do here is help an expansion across you can do an expansion across two scenarios, two points, or actually 3 points, right? You can have expansion across this point here, it's got 3 number of zeros, again this got 2 number of zeros, again this got 2 number of zeros, right? The best way but here is this one, right? Because it's got 3 number of zeros. So you can actually write this, if you want to write determinant of A in terms of cofactors. Now so the best one to use in this scenario is this third column, and we can write this expansion as nothing but equals to A. So this is the first row, so this got here is A1 3 C1 3 plus A, so you got here is the second row and the third column, so A2 3 and C2 3, and again you got here as A N 3 and C and 3, right? So in this case actually 2 is N is 4, so it is 3 4 3 A4 3 into C4 3. Okay, now since we know that this is this only thing that we have to calculate is this one, so it becomes 2 times minus 1 into 1 plus 3, and again you got here as determinant of C1 3, so you got to remove the first row and the third column. You all left here is minus 5 minus 7 2 0 3 minus 4 minus 5 minus 8 minus 3, and you got here is 0 5 and minus 6, right? And again sorry, I think I accidentally wrote it this one, sorry about that. And again so you got here 0 3 minus 4 minus 5 minus 8 and minus 3 and 0 5 minus 6. So we expanded from this column here, so you got here 2 into minus 1 into 1 plus 3, and again when I open that from here, so it becomes 0 times, so I'll just write it in the full terms so you can understand this thing here. So you got here minus 8 minus 3 5 minus 6, and again if I write this here, so it becomes plus minus 5 times minus 1 into, because this is now 1 1, and again this is your 2 1, so it becomes 2 plus 1, and this is becomes 3 minus 4 5 and minus 6, and the last one here is again this 0, for this is minus 1 times 3 plus so you got here is the third row and the first column, and you got here 3 minus 4, and again you got here is minus 8 and minus 3, right? Sorry if some portion got blocked. And again see here, this one is 0 because it is multiplied by 0, this is 0 because it is multiplied by 0. Only thing you are left here is minus 1 to the power 4, which is equals to 1, and again which is here, so minus 5 into minus 1 to the power 3 is minus 1, so it becomes plus 5. So again this is 5 times, so 6 minus 6 times 3 is minus 18, and 5 times minus 4 is minus 20, so minus 18, and there's a minus sign between, so minus and minus becomes plus. So minus 18 plus 20, you got here answer is 2, so this is 2. So actually your answer is now 5 into 2 10, 10 into 1 10, 10 2 is 20. So this is determinant of A is 20, right? So I hope that most of you are now clear about the use of the cofactor expansion and its expansion across any row and any column. Since we have now discussed how to calculate determinant of A, let's look at some properties of the determinant. So properties of determinants that you can use to actually simplify the calculation of determinant. So if A is a square matrix, so the first property is if multiple of, so if a multiple of one row A is added to another row to produce a matrix B, then determinant of B is nothing but equals to determinant of A. Okay. Now, the second property is if two rows of A are interchanged to produce B, then determinant of B is equals to minus determinant of A. Okay. Now the third one is if one row of A is multiplied by K to produce B, then determinant of B is equals to K times determinant of A, right? So if you add a multiple of one row to another, right, it doesn't change the determinant, but if you interchange two rows, there will be a minus sign involved, and if you multiply one of the rows with K, the determinant will be scaled by K, right? Now, so again, let's do an example to use these properties to simplify the calculation of determinant of A. Okay. Now, let's say we have to compute A is equals to this is a matrix A, so 1 minus 4, 2 minus 2 times 8 minus 9 minus 1, 7 and 0, right? So assume this is the matrix that is given to us, right? So since we know that zeros in any rows and columns actually simplify our calculation, so we can reduce A to echelon form, and we use that property that we just discussed about determinants, and we make use of those properties and try to find determinant of A. So if I reduce this this matrix A into echelon form, right? So to do that, right, what I'll do is 1 minus 4, 2 minus 2, 8 minus 9 minus 1, 7, 0. So I'll make use of the first property, right? So if a multiple of one row is added to another row, right, it will not change the determinant. So if I multiply this first row by 2 and add it to a second row, it will not change the determinant. So it means in this case that will becomes 1 minus 4, 2, this will become 0. So minus 8 and minus 8 again becomes 0. So because you minus 8 and plus 8, and again, so that will be minus 9 and plus 4, that will be minus 5. So and again this was minus 7 and 0. And again what I can do is actually add this first row to the third row, and if I do that, that becomes 1 minus 4, 2 and 0, 0 minus 5, and you get 0, 3 here, and you got here 2, right? Now, so you can see here this is more kind of acceptable form, because if I expand this across the first column, I can do the cofactor expansion across the first column, the calculation will be quite easy, right? So that becomes 1 into minus 1 times 1 plus 1. You got here 0, minus 5, 3 and 2, and that equals to 1 into minus 1 square 1, and that is 2 times 0, 0, 3 times minus 5 minus 15, and again there's a minus sign, so that becomes 15. So the answer here is 15, right? So this is how easily I can actually calculate this this determinant using the properties of A. Okay. Now, it is sometimes the next example that we will do. We will see that it is common use of theorem of the properties of C to factor out any common multiple of one row of the matrix, right? So let's do that example to illustrate this third property. And that is slide number 8. Now, so I've been let's say try to find compute A equals to 2, 3, minus 3, 1, minus 8, minus 9, 0, minus 4, 6, 5, 1, 0, 8, 10, minus 2, and 6. Right now, what I can do is actually take 2 out from the first row, right? So if I do that, right, that becomes determinant of A is equals to 2 times 1 minus 4, 3, 4, and 3 times minus 9, 5, and 10, minus 3, 0, 1, minus 2, and 1, minus 4, 0, and 1. Right, I mean, I've taken this 2 out because what I can do now simply here is I can reduce this into an echelon form, and I'll just multiply the first row with 3 and add it here, subtract it from the second row, right? Will not change the determinant. Now what I can do is multiply this first row again by 3 and add it in this row, right? It will not again change the determinant. And again, if I subtract the fourth row from the first row, it will again not change the determinant, right? So if I do that, right, so and do all these calculations and keep on doing this process, right, I can reduce this thing to an echelon form, and you'll find out when you do that, right, and you can take that as an example for your practice. So this is 3 minus 4 minus 2 becomes 0, 0, minus 6, 2, 0, 0, 0, and 1. When you do that, that answer simply becomes 2 times 1 into 3 into minus 6 into 1, and that comes out to be minus 36. Right. So by taking out this factor out of 2, right, we have simplified the calculations that we were going to do further. So sometimes it is, I think, recommended all the time to actually make this thing as 1. Okay, now you can subsequently do that for other matrices as well. Okay, now if you make this matrix A, like in the example, as a triangular matrix, or sorry, a diagonal matrix, or I mean, in any case, the product actually of these diagonal entries will determine the determinant of this matrix A. So what we are saying here is that if A is a triangular matrix, either triangular matrix, then determinant of A is the product of the entries on the main diagonal of A. Okay. Right, so you can use that property to actually make A as a triangular matrix, and then the determinant is simply the product of the diagonal entries. Okay, now suppose now a square matrix A has been reduced to an echelon form U. So A has been reduced to an echelon form U by row replacement and row interchanges, right? This is always possible. See that that if there are let's say R row interchanges, then we can say that determinant of A can be written as -1 to the power r determinant of actually u. Now since u is in echelon form, it is triangular, right? And so determinant of u is nothing but the product of the diagonal entries of the matrix u, which is nothing like, say, let's say u11, u22 up to u2n, right? And say if A is invertible, right, it means its determinant is not equal to 0, or it doesn't contain any linear dependent vectors. Then we can write this determinant of A as nothing but equals to -1 to the times r into the product of pivots in u, right? So the pivots in u, we know that is u11, u22, and so on and so forth, right? So even A, of course, the condition here is that A is invertible. And if A is not invertible, it means there is some linear dependent vectors, rows and columns. So when you convert into an echelon form, right, those linear dependent vectors actually becomes generates 0 entries at the diagonal, or sorry, actually 0 entries across the whole column or the whole row. In that case, for example, any diagonal element also becomes 0 with that, due to that dependency. And of course, because the determinant is nothing but the product of the pivots in u, right, so any entry being 0 in that diagonal, right, will actually make determinant A equals to 0. So if determinant A will be equal to 0 if A is not invertible. So A is not invertible. Okay, so we can actually say that there's another theorem that relates to the invertibility of this square matrix, is that a square matrix A is invertible if and only if determinant of A not equal to 0, right? This is also in the theorem. So to illustrate what I just discussed with you, right, so if I want to find the determinant of this thing here, 3, 0, -6, -5, -1, 5, 7, and -8, 2, -3, -7 and 0, -5, -6, 4 and 9, right? So this determinant here, A, I can say this determinant here, right? So what I can do is actually take this first row and simply multiply this with 2 and add it in this one. So if I do that, that becomes actually 3, -1, 2, -5, 0, 5, -3 and -6. And when I do that, right, so multiply by 2, add it here, that becomes 0, right? And right now this is 2 -2, and this is 7, so that becomes 5, so 4, and becomes -3, and this become again -10, and plus 4, that becomes again -6, right? Now if I add the second row, subtract the third row with the second row, that becomes 3, -1, 2, -5, 0, 5, -3, -6, 0, 0, 0, 0, -5, -8, 0, and 9, right? Now the thing here is since you can see here this is 0, right, all 0, it means what we are saying here is this vector actually can be written as a linear combination of this vector, and this row vector, and this row vector. Now you can actually prove that by simply taking this as a vector, this as a vector, and this as a vector. So when you try to find ax is equals to 0, right, in this scenario you will find that you will have a value for x1, x2, and x4, x3, and x4, and that will force equal this make equal to 0. So it is kind of linearly dependent. Okay, now in this case we know that because again we can force that to this to be 0 and make it lower triangular, but since I mean ideally if I do the cofactor expansion across this row here, right, so all these things will be multiplied by 0, since determinant of A is determined by the cofactor expansion of any row and any column, right? So it means if I try to calculate from any row and any column, this should be equals to the expansion from the third row. In this case this would be equals to 0, and from the dependency point of view I actually told you that if there are linear dependently row vectors or column vectors, the determinant will always be equal to 0. Okay, so what we can do it here as well for large matrices. Let's say for example you can use the properties in a recursive manner, and let's say if I have to do this calculation here, which is quite a big one in this case, which is 0, 2, 0, minus 2, 1, 5, 3, minus 5, 2, minus 7, 6, and 4, minus 1, 3, 2, and minus 2, right? So what I can do is to determine this I can actually add this the second row to the fourth row, right? Doesn't make a difference to determinant, so it means this becomes 0, 1, 2, minus 1 becomes 2, 5, minus 7, and 3, and 0, 3, 6, and 2, and if I add that becomes 0, that becomes 0 again, that becomes minus 3, and that becomes minus plus 1. Now actually can expand this across this one, so it becomes 2 into minus 1 into 2 plus 1, right? And so this one, second row, this one here, so you have this as A11 and again A21, so I can have an expansion across this one, so this is nothing but equals to got here as 1, 2, minus 1, 3, 6, and 2, and 0, minus 3, and 1. Okay, now that should be equals to, now the thing here is you can do the same thing here as I did for the bigger matrix, because adding any row, multiple of one row to another row will not change anything, right? So I can multiply this one as 3 by 3 and add it in separated from the second row, so that becomes minus 2 times 1, 2, minus 1, and 3 times it becomes 0. So if I multiply with this 3, that becomes 0, and 3 and minus 3 is 2 minus 3 becomes 5, and this becomes 0, minus 3, and 1. So now I can have a cofactor expansion across this row, which leads me to minus 2 into, again, so if I do the cofactor expansion across here and here, right, so that becomes minus 1 times, so this element is actually 2 plus 3, and multiplied with again 5 into 1, 2, 0, and minus 3, right? So that leads me to minus 2 into minus 1 into 5 into minus 3, 0, it comes minus 3 into minus 3, that becomes minus 3 into 5 minus 15 plus 15, and then becomes minus 30. Right, so this example demonstrates that if you're dealing with bigger matrices, right, so you can use the properties of determinants to actually simplify the calculation here, right? Otherwise, to do the normal calculations without reducing the matrix can be very cumbersome, and it will take a lot of time and a lot of effort to calculate the determinants. Okay, so it is best to use the properties of determinant, or even, let's say, to reduce that matrix to an echelon form, or let's say even reduce echelon form to simplify the calculation of the determinants. Okay, right. So this is the point where we'll discuss the column operations, and why we are discussing the column operations, because what we are actually trying to demonstrate here, that so we can perform, let's say, operations on the columns of a matrix in a way that it is very similar, or actually exactly similar to the row operations that we have just did for to calculate the determinants in the above examples. Now, say, to do that, right? I mean, one can show that this is a theorem again, that if A is an n cross n matrix, that determinant of A transpose, right? And you know A transpose, how you get A transpose? A transpose nothing but you replace the rows with columns of this matrix A. Now, so you can actually, because this determinant of A transpose is equals to determinant of A, I mean, you can look at the book and see the proof of it, but I'm actually going to talk about only the use of it, right? So since determinant of A transpose is determinant of A, right? So if you do so the rows in A is nothing but columns in A transpose, right? So if row operations that we are doing using the properties of the determinants that we just discussed, right? So if you see that, right, it is analogous to the column operations in A transpose, right? So it means we can say that row operations, you can perform column operations in a very similar manner as the row operations, and they follow the same properties as the three properties we discussed earlier, that if you add a multiple of one row to another row, actually it will not change the determinant. Similarly, if you add a multiple of one column to another column, right, it will not change the determinant. So if you change rows, you will change the sign of the determinant, but similarly, if you change the column of the matrix, you have to change the sign of the determinant. And again, if you take multiply any row with k, the determinant is k times the determinant of A. Now, but if similarly, if you multiply a certain column with k, right, the determinant becomes k times the determinant of A. So in this case, the row operations are I mean, if you do row operations, if you do column operations in a matrix, it will follow the same set of properties, all right? So this actually helps a bit in actually reducing the matrix A to a form in which you can easily calculate determinant of A. Okay. Now this marks the end of this lecture. Okay. Now in the next lecture we will talk about few more properties of the determinant. So I hope that you have grasped this concept of determinants and the properties, and how to use the properties to easily calculate the determinants of a matrix. Okay. Now, hopefully in the next lecture we'll talk about more properties of the determinant that will help us in simplifying the calculation of determinant of A, and hopefully in the next lecture we'll talk about the physical significance of the determinants. Okay. Shukriya. Allah Hafiz.